Hi everyone, thanks again for staying with us and welcome to AWM Pitt Grad Seminar. Our next speaker is Rui Fang. She is a PhD student from University of Pittsburgh. Her topic today is Ensemble Monte Carlo penalty finite element method for the Navier-Stokes equations with random forcing and initial conditions. Rui Fang, you can proceed.
All right. Can you guys see my screen?
Yes.
All right. Hello, everyone. My name is Rui. I'm a grad student from the University of Pittsburgh. My advisor is Professor Layton. First, I want to thank you for Jana and Professor Lavaska for inviting me. I'm excited to share my work with you. Today, I will talk about an ensemble penalty method for the Navier-Stokes equations. Can you guys see this? Okay, maybe I should. Okay, how about now? Let me figure out how to go to the next page. Okay. Oh, all right. So I want to start with a video that I took of Niagara Falls when I traveled to Canada this summer for a conference. Okay, so the biggest wave is about 3 to 5 meters long, and the flow is very chaotic and unpredictable. Since I just gave a talk on the modeling of fluid flow, and I naturally thought about that our knowledge of the fluids is so little, and there's so many things for us to discover and study. And today, I want to address a problem that numerical simulation means whatever you do, you have a finite predictability horizon, which means you have the best programs on the biggest computer after a certain amount of time, and you have it has essentially become a random number generator. So a few examples, that's why we don't have an accurate weather forecast for more than 7 days. And that's why we couldn't predict the turbulence on the airplane. This is due to the chaotic nature of turbulent flow. Perturbations of initial conditions grow exponentially until they differ in the first significant digits. This phenomena is referred to as the butterfly effect. Here is an example which makes it clear. This figure was generated by the data of a numerical test I was doing. It's a flow between offset cylinders with two realizations of perturbed initial conditions U1 and U2. This figure measures the spread of ensemble members given small perturbations. Okay, this figure measures this. Oh, sorry. This figure measures the spread of ensemble members given small perturbations on the initial conditions. I calculate the ratio of the L2 norm of the difference of U1 and U, and the norm of velocity after reach the steady state. So the blue curve is the difference between U1 and U, and the red curve is the difference between U2 and U. The green curve is the difference between U and the average of U1 and U2. The black curve is the difference of U1 and U2, and which the black curve gives the spread. So we can see from very beginning, U1 and U2, they are nearly identical. However, after time progresses, the difference amplifies and the flow trajectory start to diverge. Okay, so chaos limits the predictability. The goal is to extend the predictability horizon. To do that, we need ensemble simulation with more realizations. So we are facing a barrier in the amount of storage, and we have the amount of computation resources. The idea is to solve the Navier-Stokes equations with perturbed initial conditions and possibly other data like the force, viscosity perturbed too. The average of the realization extend the predictability horizon. Oh, sorry. Oh, how to go? All right, yeah. So Navier-Stokes equations cover the fluid motion, and many of you may have heard that it's one of the millennial prize problem. And for 3 decades, and given the initial conditions, mathematicians have not yet proved the smooth solution of its exist. It's a complicated PDE system, but every term has a physical meaning, and I want to show you the derivation. So first, I want to start with divergence U equal to 0. It's based on the conservation of mass. If mass is conserved, the rate of change of mass in a volume must equal to the net mass flux across the boundary. And we can apply the divergence theorem. We will have the integral on the domain partial rho partial t plus divergence u rho times u equal to 0. And if we shrink this volume to a point, we will have things we are dealing with incompressible fluid. So the density is a constant. And if we shrink the velocity to a point, we will have divergence u equal to 0. And next is the conservation of momentum. This is basically this is the Newton's second law. Force equal to mass times acceleration. And if you look at this PDE, the partial u partial t plus u dot grad u, I call it in red. This is actually the acceleration. We can consider a particle at time t is at position x. After delta t time, it flow up to x plus u times delta t. If we take delta t, we send delta t to 0, we can have the acceleration, which is the change of the velocity. We will have partial u partial t plus u dot grad u. And since Newton's law, second law, we already have the acceleration. What are the forces we have? So there are 2 kinds of forces. One is internal forces. I colored in blue. So pressure, gradient of the pressure. So the flow have a tendency flow from a higher pressure to a lower pressure. And another term is negative nu Laplacian u. So that's the friction. When we can apply the friction, when we apply the divergence theorem, we can have the Laplacian u. And the other part is the external force, which is F. Say gravity is external force. Okay, now we have an understanding, a basic understanding of the Navier-Stokes equations. The question is, how do we compute on a computer? Today, I want to introduce a finite element method. To start with, I have a 1D domain, so that's a line, and then I can split the line into many small pieces. We can approximate this curve, the black curve, with piecewise linear functions, and we can tell it gives a really good approximation. And so we also introduced the basis functions. If you look at the graph on the right, we are having 6 nodes, and then I define the basis function for each node. Say phi1 is equal to 1 at node 1, and the other nodes is 0, and phi5 is 1 on the node 5 and otherwise 0. So it looked like a head. So we can call this a head function. And this one is a 2D case. This is a polygonal we have, and then we are using the triangle to have the mesh. And similarly, we have phi j equal to 1 at the jth node, and other nodes they are 0. And this picture was taken from Professor Layton's book. And also, this is a linear basis function. In practice, we also use quadratic polynomials to have a better approximation of the function. All right, now back to the model. I want to talk about the algorithm I'm using. Here is the same picture of a flow between offset cylinders with only 2 realizations. As I calculate the relative error, the ratio of the L2 norm of the difference and the norm after it reached steady states. And looking at this, when the first significant digit is trustworthy, reading across, the black curve represent the predictability horizon of a single realization, and it's about time 30. The green curve is the predictability horizon of the average. It's about time 50. So with only 2 realizations, we have extended the predictability horizon. The challenge, of course, is how to have more realizations, given limited storage and computation resources. So the method we are using in analyzing is based on 2 ingredients. The first ingredient is in ensemble algorithm. That means we have a shared coefficient matrix. We have a discretization of the nonlinear term, which I colored in red. And the new time level Tn plus 1 is driven by the mean and not by the variance. So that's why we only need to store 1 coefficient matrix at a time. The second ingredient is we use the penalty approach to eliminate the pressure. Remember, we have the divergence U equal to 0. Now, instead of having div U equal to 0, we can approximate div U with negative epsilon times the pressure. Epsilon is a very small number, and we can eliminate the gradient P equal to negative 1 over epsilon times the gradient times a divergence of U. And the classical choice of the penalty parameter epsilon is we set this equal to the time step. Now come to the model. We choose the velocity space to be H10 and the pressure space is L20. We use the backward Euler in time, which is the first term. Which is the first term. Since we have the explicit discretization of the stretching term colored in red, a time step restriction is necessary. Hence, the CFL condition is written here. The analysis is as follows. On this slide is a summary of the main point of my paper. The theorem we proved is under the CFL condition, which depends on the fluctuations, not on the mean flow. We proved that the method is a nonlinearly long-time energy stable, and using that, we proved the optimal error estimate as dot x, dot t, and the penalty parameter epsilon goes to 0. We also interest in the Monte Carlo as the number of realization increases. So we prove that the optimal Monte Carlo convergence as J goes to infinity. We also developed a suite of numerical tests which confirm that the theorem is sharp. So here is the detail. The statement of the stability. We prove that the norm of velocity is bounded by a finite number. And if we look at the right-hand side, is the first term is the force and the initial conditions, which are known and finite. Next, this is the theorem of the convergence. So first, the arrow is colored in blue. We notice that the arrow is growing exponentially with the initial condition, which on the second row colored in red. And I also highlight the h squared and delta t. So since we are using backward Euler, in H1 in space, we observe that order 1 in time and order 1 in space, which is optimal. Similarly, we extend the stability and convergence theorem to the Monte Carlo approach, which is omitted here. Now I will talk about the test we did. First is the convergence test. To calculate the convergence rate, we used the Green-Taylor vortex with analytical solutions stated below. We interpolate the initial condition. In the test, we took two realizations with small perturbation, epsilon equal to 10 to the negative 3 and a negative 10 to the 3. 10 to the negative 10 to the negative 3. And for the parameter setting, we have the Reynolds number equal to 1. Final time is 1. Mesh size is 1 over m. Time step is 1/10 of the mesh size, which is a constant. The ratio of mesh size and the time step is a constant. We choose the classical penalty parameter equal to the time step. And to calculate, we calculate the error at two successive values of h by assuming that error is equal to a constant times h to the beta power. From this table, we can see that the convergence rate for U1 and U2 are first order as expected. We also did stability verification. We used flow between offset cylinders. Okay, the domain is a disk with a small offset optical inside, and the flow is driven by the counterclockwise rotational body force on the inner circle. With no slip boundary conditions, the flow is at rest at the beginning, and we add some perturbations of the initial conditions in a way that no slip boundary condition is preserved. We took the constant C value from Layton's paper. We calculated some statistics. From the entropy figure, we can see that they have a very similar pattern. The average seems like have a little, the average one seems have a little less vorticity, which is the black curve. And we also calculate the angular momentum and the energy. They align very well. We didn't perturb on the force. That's a reasonable reflection. And these figures show that under the CFL condition is sufficient for the stability at Reynolds number equal to 150. All right, here is a summary. We proved the nonlinear long time energy stable and optimal error estimate. We extended to the Monte Carlo. Also, we did numerical tests to confirm our theorems. Last but not least, I want to thank you for listening to my talk, and be delighted to discuss this work with any of you. There's a lot interesting direction that I can go. Currently, we are working on the higher Reynolds number. Here is my email. please contact me if you have any questions or you want to discuss later. And yeah, recently we also submitted a paper about turbulence model to computers and fluids, and I posted on the archive. You can see my paper too. All right, thank you guys. Any questions?
Thank you for the talk.